Welcome back to our machine design series. We're continuing our discussion of shafts today, picking up where we left off last time. We had just started talking about vibration of shafts. And so let's dive into this topic, critical speeds of rotating shafts. And to start us off, just want to reiterate some definitions that you should know already from any dynamics class that you may have taken, but just to get us all on the same page. First, we need to define what we mean by free vibrations. So free vibrations of an elastic body, which is also known as natural vibrations, occur at the natural frequency. And again, I'm going to denote that with this omega sub n. So, free vibrations. This is what happens when you pluck a guitar string and it continues to oscillate naturally without any additional external forces. You could also think of pulling a child back on a swing and letting go, and they continue to go back and forth. If there was no friction, air resistance, they could go back and forth forever. And that frequency at which they move back and forth, or at which the string on your guitar moves back and forth, that's the natural frequency of that system. All right, now forced vibrations occur at the frequency of an applied force. Okay, so when your phone vibrates in your pocket, there is a motor inside of your phone that is causing an offset mass to move back and forth at a forced frequency, and that's causing that forced vibration of the phone in your pocket. Now, if the forced frequency is equal to the natural frequency, the vibration amplitude increases manyfold. And this phenomenon is known as resonance. Okay, so resonance, something we're usually trying to avoid, happens when our forced vibration frequency is equal to the natural frequency. And that goes back to our best practice that we talked about last time, where we want this first natural frequency of our shaft to be at least 3 times higher than the highest forcing frequency, so that those two different frequencies stay far away from each other. and we avoid this problem of resonance. Okay, so now let's talk about how we figure out what the natural frequency is. The forced frequency is going to come from your loading, so that's going to be either given to you in a problem statement, or if you're working in industry, that's going to be given by the motor that you're running or the loading that your analysis team has worked out with a different type of analysis. So to figure out the natural frequency of the shaft that we're designing, we can idealize our system as a simple mass spring system. So if you've taken a dynamics class, you definitely should have seen something like this before. We've got a mass sitting on top of a spring, which is attached to the ground. And this mass is going to move back and forth with some deflection we call x. And the natural frequency of this system is the square root of k over m. So square root of that spring stiffness divided by the mass. So the mass is going to come from the mass of your shaft, right? Because remember that what we're doing here is we're making a model of some shaft that we've designed, and we're saying that it's equivalent to this mass spring system for the purposes of our vibration analysis. Okay, so the mass is just the mass of this shaft, but now how do we get to an equivalent stiffness of this shaft? That's going to depend on the loading and the constraints that are imposed on your shaft. So equivalent stiffness. We'll go over just a few different types. There's many more than this, but here's 3 of the common ones. So first, we'll just talk about an axial load. Okay, the equivalent stiffness of this shaft is Young's modulus of the material that it's made of times the cross-sectional area divided by the length of the shaft. Simple enough. Okay, now let's have a fixed end condition and a transverse load in the middle. For this scenario, our equivalent stiffness is 192 times Young's modulus times I, which is the area moment of our cross-section, divided by the length cubed. And then lastly, let's talk about a cantilever with a load on the end, and that equivalent stiffness is 3 times Young's modulus times I divided by L cubed. Okay, and right away we can see a few things from these equivalent stiffness equations. One is that, remember when we were going through our best practices list, and I'll scroll up so we can find it, we said that to minimize deflection, we wanted to keep the shaft length as short as possible, right? Okay, so now that we have this equivalent stiffness, we can see exactly why. If this length is made smaller, our stiffness is going to go up, which means that for the same amount of load, we're going to get less deflection because we have a higher stiffness. And when we have a loading scenario like one of these two, that relationship is actually exponential or cubic. So as I decrease the length here, that length is cubed, and so this number in the denominator is going to get small really fast as I decrease the length, which means that the stiffness is going to go up really fast as I decrease the length, which means that deflection goes down. So there's a strong dependence on the length of the shaft to stiffness and therefore deflection. Okay, so with that, just a couple strategies we can use to avoid resonance. Okay, so with these equations, you will be able to work out the natural frequency of a shaft. And once you've done that and you have your forcing frequency, your goal is going to be to keep your forcing frequencies below the system's first critical frequency. Okay, in other words, you want to keep your forcing frequency below this first natural frequency of the system. Okay, next, if that's not possible, if you need to have a forcing frequency that is higher than your first critical frequency, one strategy you can try is to accelerate the system rapidly through the resonance. Okay, so if you absolutely need to get to a forcing frequency that is higher than the first natural frequency, you can accelerate that system from rest to the forcing frequency that you're aiming for. If you do that rapidly, you may be able to pass through the resonance before the vibrations have a chance to really build up amplitude. Okay, and so with that, that's all that we're going to discuss regarding the critical speeds of rotating shafts. And in the next video, we'll start talking about some mechanisms that are commonly used to attach shafts to hubs of many different components. So I look forward to seeing you in the next video. Hope you enjoyed this one. Thanks again for watching.